Oh, we've been able to do a fair amount with PChem and thermodynamics and statistical mechanics in predicting what chemical and physical systems will do. But unfortunately, so far, we haven't been able to predict much about any actual chemistry. What I mean by that is we've been able to predict state changes, meaning if the temperature and pressure change, we can understand what happens to the thermodynamic energies or predict whether something is spontaneous or not. We can also predict things about phase changes, changes of phase like solid, liquid, gas. So we can predict an awful lot now about melting and boiling and freezing and evaporation. But we haven't said anything about any actual chemical reactions or equilibrium chemical reactions. So the next goal is to be able to use the tools we've developed with thermodynamics and chemical potentials and partition functions to be able to explain what happens in a chemical reaction where molecules actually change from one chemical species to another. So you know a fair amount about equilibrium already from general chemistry. For example, you know an equilibrium constant is the amounts of products divided by the amounts of reactants, but we'll be able to answer questions like why the equilibrium constant takes this particular form and why some reactions are equilibrium reactions and some proceed to completion or some don't proceed at all. So for example, take this reaction written here. Hydrogen gas and bromine gas, and I've written this with an equilibrium arrow, forming two HBr gaseous molecules. So the equilibrium arrow, of course, means that what we know if we do this experimentally at, say, a temperature of 1000 Kelvin, is that when we mix hydrogen and bromine gas together in a reaction vessel, some of the hydrogen and bromine will react, but not all of it. We'll form some HBr, but the reaction won't necessarily go all the way to completion. So the question we have to answer is why would this reaction not go all the way to completion? Why does it go partway and then stop? And based on what we know about thermodynamics so far, we can expect that this happens for a reason that we can describe in a number of different ways. The reaction, if the reaction didn't proceed at all, so let's see, what I'm plotting here is the free energy, the Gibbs free energy. If I do this reaction at constant temperature and pressure, what we expect is the reaction goes forward at the beginning because that lowers the free energy, but it only proceeds to a certain point, maybe whether that's 5% to completion or 1% to completion or whatever that number is. It stops at a certain point because beyond that point, the free energy would increase. And we know that the system will always, at constant temperature and pressure, will always proceed in a direction that lowers the free energy of the system. There's a lot of different ways of making that statement. I could say that we minimize the free energy of the system. I could say that we maximize the entropy of the universe. I could say that this state is the most probable out of all the possible states. So all those are different ways of saying the same thing. Turns out the way that's going to be most convenient for us to think about this is not in terms of free energy necessarily, but in terms of chemical potential. And what we'll discover is that at this point where the free energy is at a minimum, the chemical potential of the reactants and the chemical potential of the products are equal to each other. I don't gain any chemical potential by converting reactants to products at this point. So this is just a general overview of how we're going to be thinking about equilibrium problems from a physical chemistry point of view. And the next goal is to use the PChem tools that we've developed so far to understand how exactly to predict how far an equilibrium reaction will proceed.